All right. So today we are going to see a new topic, that is finite state machines and the sequential logic principles. You already have learned the state machine design in your lower classes, but I am assuming that you need some kind of refreshing for that topic. So I'm starting right from the beginning. At the same time, we'll encounter some interesting concepts which you may have done already, or maybe you don't know about it as yet. So we'll start with the finite state machines. So basically, a finite state machine is classified into two categories. One is called as any digital circuit is categorized into two categories. One is the combinational circuit and the other is a sequential circuit. What exactly is a combinational circuit? Whatever we have done till now using VHDL, we are talking about combinational circuits most of the time. So what is a combinational circuit? It is one whose outputs will depend only on its current inputs. This is very, very important. Okay. So how do you define a combinational circuit? Combinational circuit is one whose outputs will depend only on its current inputs. Another category is the sequential circuit, digital circuit or logic circuit. So in this particular circuit, its output depend not only on the present inputs, that is the current inputs, but also on a past sequence of inputs. This is what makes it different than the combinational circuit. So you can see very clearly the distinction is that the output is computed, or let us say the output is generated based on the current input, whatever is the current input, and also on a resistors is used to store these inputs. So whenever you see sequential design or sequential logic, there has to be a flip-flop. Okay, is that concept clear to all of you, guys?
Yes, sir.
So you should now be in a position to distinguish between a combinational circuit and a sequential circuit. Okay, so in sequential circuit, it is impracticable to describe the behavior by means of a truth table. Please remember that we were talking about, when we were talking about combinational circuit, a very simple thing was to describe the behavior in the terms of the truth table. But it is not possible, or it is impracticable to describe the behavior of the sequential circuit by the means of by the means of a truth table. Okay, which would list the outputs as a function of input sequences that have been received till the current time. So that is not possible. So you'll never have a truth table for a state machine or for a sequential circuit. Instead, it is let us say advantageous to have or to know the current state of the circuit, and that is where the state machines come into existence. So we'll look at the basic terminologies. What exactly is a state? The state of a sequential circuit is a collection of state variables whose values at any one time contain all information about the past necessary to account or compute whatever for the circuit's future behavior. So that is the definition of state. So these are the textbook definitions. Please remember these definitions properly. Okay. So what exactly is a state? It is a collection of state variables at one particular given time. Okay, which contain all information about the past. Now, what do we say? Why do we say that it contains all the information about the past? Because naturally, these particular outputs or states are computed based on the previous states. So naturally, up to the current state, whatever was the situation, whatever was the condition, whatever was the state, is all captured in this particular state of the circuit. Then what are the state variables? These are simply the binary variable values corresponding to certain logic signals in the circuit. We'll see with an example. So a circuit which is having n binary state variables has got 2 to the power n possible states. Please remember this. Very, very important concept here. Therefore, the states are finite, and hence sequential circuits are also called as finite state machines. So why they are called as finite state machines? Because the states are finite. Remember that. It doesn't mean that finite means small number of states. The states can be large, huge number, but of course they are finite. They are not infinite. Then the most important thing that drives the sequential logic circuit is the clock. The state changes basically will happen or occur at specified times with the help of a free running clock signal. So the clock is the heart of sequential state machine or a state machine. Two types of clock signals are there. Basically, one is called as the active high clock. Naturally, these are those clocks if the state change will occur at the rising edge of the clock. Okay, and obviously the other way around, active low clocks are those if the state changes will occur at the falling edge of the clock signal. Here you can see that the state changes are happening at the rising edge of the clock. Okay, so the state changes will happen at these parts, not over here or over here. Okay, in the other variety, the state change will occur over here or over here. All right, so that is how we can say that there are two types of clocks, active high clock and active low clock. Now, what are the delays in sequential circuits? The rise time and the fall time. This is a very, very important thing. The rise time refers to the time it takes for a voltage or current to rise from 10% to 90% of its peak value. Now, we know this particular concept of rise time from, let us say, the switching circuits or maybe the switching waveforms when you look at the performance of transistors as switches. Okay, so here the definition is the time that it takes for voltage or current to rise from 10% to 90% of its peak value. Similarly, the fall time, or also called as the pulse decay time, it is a time required for the amplitude of a pulse to decrease or fall from a specified value, usually 90% of the peak value, exclusive of the overshoot or the undershoot, to another specified value, which is 10% of the peak value. So one rise time, you can have the rise time as the time taken for the signal to rise from 10% to 90% of the peak value, and conversely the fall time will be from 90% to 10% respectively. Again, one important point to note here is that the rise time and the fall times may not be symmetrical. Okay, it depends on the geometry of the device, in the sense the design of the device. Okay, so we can say that the rise time and fall time need not be symmetrical. They need not be the same. So this is what the rise time and the fall time is about. So I have shown a buffer. Okay, so whatever is the output, you can see the input basically over here in the form of the gray waveform. So this is the input, and you'll see that there is a slight delay, and from here you can see that it takes some finite time because the slew rate is not infinite. It takes some finite time for the pulse to rise up, and this is called as the rise time TR. Similarly, it doesn't immediately go down to zero if it is switched off, or the signal returns back to zero, original signal returns back to zero, but again from 90% to 10%. This is called as the fall time. Now these play a very important part in the actual working of the state machines, because everything happens at the rising edge of or the falling edge of the clock. What are the factors affecting the rise and the fall times? They depend on the on resistance of the transistor and the load capacitance. Now, this is explicitly dominant or predominant, let us say, in case of any device, but mostly in terms of the CMOS devices. Okay, in MOS device, if you see the transistor, the P channel or the N channel MOSFETs, those were used. So it's a combination of PMOS and NMOS both. If you consider the technology of CMOS, in that case, the on resistance of the transistor is different, will be there into picture, and at the same time the capacitance. Now, how does this all tie up? Okay, let us say on resistance. Now, I don't have the illustration here, but just imagine that you have a transistor and it's a MOS transistor, obviously, and naturally it is cascaded to another MOS transistor as the output. Now, depending on the on resistance of the transistor, which becomes R, and the capacitance between the gate, okay, and the body of the transistor, that is the gate capacitance, this form what is called as the RC network. Okay, and naturally, you know, the characteristic of RC. In case of RC, the rise time and the fall times will be different. Rise time obviously happens in an exponential fashion. Okay, similar is the case with the fall time also. So that is where the rise time and the fall time creep into your devices. Okay. Also, stray capacitance will play an important role. If the gate, in addition to the gate capacitance, there may be some capacitance, stray capacitance, because of some parallel line going over there between this and the between the output and the ground. Okay, so it will determine, it will also determine the rise and the fall times. Okay, and this particular stray capacitance will be there because of the output circuits, including gates, output transistor, internal wiring, packaging, interconnects, and including the transistors, internal wiring, and packaging. So all this will may give rise to stray capacitance. So this is the basic culprit, or the, let us say, a group of culprits which is going to affect the rise time and the fall time. All right. Next is the propagation delay. It is the amount of time starting from when the input to a logic gate becomes stable and valid. This is very all right. Am I audible and visible too, guys?
Yes, sir. It's audible now.
Okay. So the next is the propagation delay. It is the amount of time starting from when the input to a logic gate becomes stable and valid to the time that the output of the logic gate is stable and valid. Remember these two words, stable and valid. Propagation delays are denoted as epsilon or simply as TPHL and TPLH. Now, in one of the assignments, I hope all of you have got the assignment list.
Yes,
Yes.
sir.
Have all of you got the assignment list?
Yes, sir.
Okay.
Yes,
So in
sir.
that, one of the assignments is that you are supposed to model an already existing device, 7400 LS7400 74LS00, which is an AND gate, which is manufactured by some company like Intersil or something like that. So in that data sheet, they also mention this TPLH and TPHL. Okay, so that is what you are supposed to model using VHDL. But then these are the actual behavior of the devices, that there will be some propagation delay, and these are denoted by epsilon or TPHL and TPLH. Factors leading to this non-zero propagation delays are the semiconductor physics, we already know. Then the circuit environment, including input signal, transition rate, that is the clock frequency, input and the output capacitance, let us say the loading. So all this contributes to the propagation delay. So remember, the rise time, fall time, and the propagation delays are the two important delays which will come across in digital logic circuits. This is how you can show the propagation delay. Here I have shown a NOT gate. As you can see, the signal changed from low to high here. Okay, but the output is not changing immediately. Okay, there will be some delay which is called as a propagation delay. Please remember, this is different than sorry, the rise time and the fall times. So this is what we call as the TPHL, high to low and low to high. Okay, so there will be some delays like this. These are called as the propagation delays. Now, metastability is another important thing which you may not have studied in your lower classes, but a very important issue when it comes to the stability of reliability and stability of a digital circuit, specifically when you are using a clock. So naturally, this becomes very important for the state machines. As all of you know that we have already said that sequential circuits will be flip-flops, will include flip-flops as one of the important components. And this is where the metastability may come into picture. What is a bistable component, by the way? A bistable component is one having two stable states. So flip-flop is a bistable. You know, it can be in one state, zero or high. I mean zero or low, or one and high. So it can be either of into two stable states. Okay, that is called as a bistable element or component. But theoretically, there are two stable states. A third stable state also may practically exist. We are going to see what this state is. This is called as a metastable state. Now, where is it and how will it be affected? Metastable state is defined as a state which exists between either valid digital logic states. So, it is an undefined voltage, which is the most dangerous thing. Okay, actually, there are three states of equilibrium. Two are valid in digital electronics, while the third is invalid and which has to be avoided at all costs. Since the metastable state is also equilibrium state, the circuit can theoretically stay in that state indefinitely. So, as we have said that there can be the third state, we are going to see why that state, how that particular state comes into picture. But again, this state is a very critical one because it may be affected by the electrical noise and the equilibrium will get disturbed and the metastable state is left, or the circuit will come out of the metastable state and it can go to any of the two states. That is why metastable state is very dangerous, because since electrical noise is random, you never know which state it is going to fall into. And our basic understanding for the circuit is that, sequential circuit is that, you have to know the current state so that you can predict or you can design for the next state. But if the current state itself is a metastable state, in that case, you really have a big problem there. Okay, that is where many of the digital circuits, sequential circuits will fail. Okay, now that is the reason why we have to avoid the metastable state at all cost. Okay, now we saw that metastability, this particular phenomenon is called as metastability. It is a purely probabilistic issue, as you can say, and the reliability term. So whenever we talk about any circuit, we talk in terms of its reliability. And when we talk about reliability, there is a term called as mean time between failures. Now, for an ideal device, the value of MTBF will be, yes, high or low. Guys, tell me. Guys, are you there?
Yes, sir.
So what should be the ideal value of MTBF? 0 or infinite?
Ideally, it should be 0.
0. So the circuit fails every now and then.
Oh, okay.
0 means it is always failing.
Yes, sorry. I got it wrong.
So it should
It
be
has to be
infinite.
Yes.
Or in practical circuits, this
Very high.
MTBF should be as large as possible. Maybe in tens of 20s or 20 tens of years, or tens of multiples of tens of years. So this is how we can define metastability diagrammatically. You have low state and high state, and there is an intermediate state called as metastable state. And this is where you can see here that this also is a stable state, but it can be pushed into any one of the states by a small nudge over here. Okay, and that nudge is provided by the electrical noise. And we know that the noise is random. So it can have a positive magnitude or a negative magnitude, and this state will be left by the circuit. It may fall here or it may fall here depending on whatever is the value and the magnitude and the polarity of the electrical noise. So we never know where it will fall. It is all probabilistic. How does this metastability occur? For that, we have to understand some important terms related to the flip-flop. Okay. One of the important parameters is the setup time TSU. It is the time required for the input data signal at a flip-flop to be valid before the incoming clock edge arrives. So obviously, we can never have, I mean, we should never say that, okay, as soon as the clock edge has arrived and the data is present, it will work properly. It may not, because the data signal has to be there prior to the incoming clock edge. Okay, so that there is some time before which it should be stable. Okay, what is the whole time? Whole time is the time required for the input signal, input data signal to remain valid after the clock edge has transitioned. We'll see this with the figure, so then we'll be able to understand properly. Then we have something called as resolve time, also called slack time or settling time. This is the amount of time the flip-flop's output must return to a valid level before it is used. Okay. Output must be valid by the next clock minus any chip or routing delay. Metastable conditions will occur when these timings like setup hold times are violated in case of flip-flop. So for every flip-flop, a metastability window is defined. This window is a specific length of time during which both the data and clock should four. Now 7474 is what a master slave JK flip-flop. All of you know that. So they will be, the manufacturers will be giving you this data in the data sheet. So you can see here for 7474, 74C74, this family of the gate for the flip-flop. The setup time is 100 nanoseconds, hold time is 0 nanoseconds. So the window is addition of these two. Okay. So as you can see here, 74S74, 3 nanoseconds, 2 nanoseconds, the total is 5. So in this particular window, there should not be any change in the signal. This is what happens in case of a typical D flip-flop. Okay. So as you can see here, before the clock edge arrives, my data should be valid. Okay. D is the input data. So it should be valid. And if this TSU and T hold both are not violated or respected, let us say the data is stable over here, correspondingly the output will be flipped to the second level, that is D. Q is equal to D. I mean, whatever is the output is asserted. Flip-flop goes high, output of flip-flop goes high. Okay. Similar thing happens over here also. Like the data is valid. So the metastability window is the data respects the metastability window. Okay. But here see what has happened. What is happening here? You'll see that slightly the data is not valid in the setup time. Here you can see that at this particular edge, you see that? All of you?
Yes, sir.
So you'll see that the data is changing from D is changing from 0 to 1 in this particular setup time itself. And that is why we will be having metastable condition. All right. This is what happens when the setup time violation is there. And a similar case will happen if the hold time violation is also there. All right. So you can see that the data has to be stable in the metastability window. All right, and then you'll see that this metastability, it has gone into metastability, but then, as I said, it will settle down into any one of the stable states because of the noise, electrical noise. Okay, and the amount of time that it requires for it to settle down is basically the additional delay that we have. Okay, so you can see that output Q is going in a metastable state, and then it will settle down into any one of the states, this state or this state. So this particular time is an additional delay, and that is there because of the metastability. What are the consequences? So metastability will spoil most of the conceptual and computational tools that we use from day to day, that is binary or two state circuits. It defies careful and accurate measurement. So you cannot actually go for accurate measurements if metastability phenomenon is there. It can produce failures, and these failures leave no trace at all. Okay, so it is not possible for you to debug also. Why the system is failing, you will never come to know, because it does not leave any trace, any trace. It can cause failures in systems whose software is correct and whose hardware passes all the conventional states. That is the most important and critical part. If your software may be correct, your hardware may be passing the test, but then the system fails. So the possibility is that there may be a metastability issue. Okay, so who is the culprit? Metastability. For causing metastability, what is the problem? What is the who is the culprit to cause metastability? Summarize. It is the violation of the setup time and the hold times in the flip flop. Remember this. So what does metastability do? It will, first of all, it will go into an, let us say, an unstable state, a metastable state to be more precise, and then it will fall down to any one of the states which cannot be determined. Okay, so if your output expected is 0 and if you are getting 1, then your circuit fails, isn't it? So that is the failure, and this failure is caused because of the metastability. In addition to that, metastability will also add to the delay. Okay, so what is the solution for metastability? Is there any? Remember that all the flip-flops and of course latches also will exhibit metastability. Now remember one thing, that metastability cannot be eliminated. This is one very important statement that you should always remember. So you have to live with metastability, but there are ways and means to make that metastability less likely to occur. Okay, since there is no direct workaround for this problem, the issues are dealt with by calculating the failure rate and engineering adequate reliability, that is mean time to failure. So the reliability of your device can be projected in terms of MTBF or MTTF. Okay, anyways, metastability cannot be avoided at the boundary between asynchronous and synchronous systems. This is logical thing, because your system input is not synchronized to any clock. It is coming from the external world. So naturally, if your signal is coming, it can come anytime. And so we cannot make sure that the setup time or the hold time windows are respected in that case. So there is a definite chance of metastability there. Where does this happen? It happens at the boundary between the synchronous and the asynchronous systems. Just hold on for a moment. Okay, all right. Guys, are you there?
Yes, sir.
Where are the others? They dropped out of the meeting. Okay, I'll continue. I'll not wait for anyone. Okay, as I said, the metastability cannot be avoided at the boundaries between the asynchronous and the synchronous systems. However, the probability that these states are encountered can be significantly reduced by the use of what are called as synchronizers or the use of faster flip-flops. Obviously, faster flip-flops will mean narrower metastable window. Or you can use something called as metastable hardened flip-flops. Now these are designed for very high bandwidth and reduced sampling times and optimized for in which you can minimize the probability of the occurrence of metastability. These are some metastability equations. You can just write them down. So MTBF is e to the power TR by tau divided by FD into FC into TO. And TR, which is TCKO plus Tmet. We already know these terms as metastability delay. TR is the total flip-flop output settling time. TCKO is flip-flop clock to out delay. Tmet is the additional settling time required for the flip-flop to go from metastable state to stable state. Tau is called as the metastable decay constant. T naught is metastability aperture. Okay, these are all mentioned in the flip-flop data sheets. FD is the data transition, it is twice the data frequency, and FC is the clock frequency. So with that, you can actually calculate the MTBF, that is the mean time between failures. This is the relationship between MTBF and resolution time. So you can see that MTBF can have to go for reliable systems, they have to go in years. Okay. Now you must have had this experience many times that many possibility is there that your smartphones need to be reset or rebooted maybe after a few months of use, or maybe sometimes it simply hangs. Okay, have you observed that kind of behavior, right?
Yes, sir.
So it is quite possible that there may be some kind of metastability issue and the internal circuitry must have gone wrong. Okay, and that is the reason why you have to simply reboot your device. Of course, that doesn't happen quite frequently. Maybe 6 months later down the line, or maybe 1 year. Sometime you have to reboot the system. Okay, so this is the basic problem. But remember that these are all consumer devices. Okay, so you can it won't harm if you even reset it, reboot it after every 1 month. But it is not the situation in some critical systems like the defense electronics. Okay, you simply have to make sure that the failure is as less as possible, or your MTBF is as high as possible there. So this is what is the relationship between the MTBF and the resolution time. These are some device parameters based on which we can calculate the MTBF. Just have a look at this. The first few devices are the flip-flops, then we have a PAL, and then we have the CPLDs. So as technology advanced, you can see that these values became smaller and smaller. And obviously, because of these values, the reliability is now much better. This is another simplified equation which I found out from literature. MTBF is given as e to the power C2 into Tmat by C1 into Fd into Fc. C1 is a proportionality constant that is similar to aperture. This is a simplified version. C2 is a constant inversely proportional to the metastability decay count. C1 and C2 values are given by the manufacturer. So it becomes very easy for you to calculate the MTBF. So these are the C1 and C2 for typical FPGAs. For ProASIC, which was manufactured by at Actel, now it is no longer manufactured, but then other devices are also there. You can see. Okay, so you'll see that C1 and C2 values are given, FC is given, and you can very easily calculate the MTBF. Now MTBF will run into years. Please remember this, and that is what is expected of a good system. So how to get better MTBFs? Or I can say conversely, try to avoid or try to minimize the occurrence of metastability. As we have already looked at the solution, use faster flip-flops. But again, this approach is incapable of coping up with the ever-increasing clock speed. How fast you will make the flip-flop? The next time the clock speed doubles, again your flip-flop design has to be upgraded. So it is very difficult to catch up with that. Second solution is wait for multiple clock ticks to get a longer metastability resolution time. This additional delay will not generally degrade the performance unless there is a critical round trip handshake. Okay, so you can have this solution of waiting for multiple clock ticks. An elegant approach is, however, to use the synchronizers to create what is called as a time buffer for recovering from a metastable event. So this is the single stage synchronizer. It is a single flip-flop which you can introduce between the asynchronous input and the synchronous system. That is, this is the external world from where the input is coming. This is your clock system, and you are introducing one more flip-flop over there to ensure the synchronization. This will improve the MTBF. Surprisingly, this is going to improve the MTBF. You will again ask whether this also will be going into metastability. Yes, but then there is a better chance because this is acting as a buffer, time buffer. Then you have two-stage synchronizer. Adding second flip-flop to the design will reduce the chance of output going metastable. This is all probabilistic, remember. Okay, but they have found out that the use of these synchronizers will minimize the probability of occurrence of the metastable state. Output from first flip-flop may go valid before the second flip-flop is clocked. This is one more. I mean, obviously, since you are using the flip-flops themselves for synchronization, they themselves may go into the metastable state. But the probability goes on decreasing. The limitation of the single stage synchronizer is that it will fail if the synchronizer output goes into metastability due to the setup and hold time violation at the sync flip-flop. Now please remember one thing. Doesn't it occur to you that this flip-flop may also go into metastable state? Yes, obviously we have said that. Then why will it minimize the probability? Think about it. Very simple solution, very simple answer to that. What is the answer? Can you tell me? Guys? Guys, are you there?
Yes, sir.
So what may be the possible answer? This flip-flop can be different. It can be a faster flip-flop. So you do not use fast flip-flops in the system itself. Only one flip-flop, which is the synchronizer flip-flop, can be fast. Are you able to understand this? Guys?
Okay. Yes, sir.
So only one special flip-flop need to be used here. Rather than making all the system flip-flops to be special flip-flops, only one fast flip-flop can be used. And that will also, that will actually decrease the probability of metastability. But of course, you can go on increasing the number of flip-flops and the probability can be decreased still further. This is the two-stage synchronizer. As you can see now, an additional flip-flop is there. Again, these are special flip-flops. Okay, so if the asynchronous input reaches a stable condition outside the setup interval, it will be clocked through with a latency of 2 clock cycles. Otherwise, flip-flop may enter metastability, this first flip-flop. If metastability is resolved in less than 1 clock cycle, that is FF2 will have, that is the second flip-flop will have a stable input. So the price that you are paying is the latency. So at the appearance of the clock, obviously this goes into output of Q1 goes into metastable condition. Okay. But then whenever it recovers, next time the output will again be synchronized. This is another alternative synchronizer design. We will not go into much details about these things. But you can see that the D input of first flip-flop is connected to VCC, while asynchronous input actually is used as a clock. Okay. Well, let us not go into the details. Another important aspect is the clock skew. Okay. So what is this clock skew? It is defined only for sequentially adjacent flip-flops that have only combinational logic or interconnect between them. Okay. So how do you define clock skew? Given two sequentially adjacent flip-flops Fi and Fj and an equipotential clock distribution network, the clock skew between these two flip-flops is defined as T skew Ij is equal to Tci minus Tcj, where Tci and Tcj are the clock delays from the clock source to the flip-flops Fi and Fj respectively. So as you can see here, there are two flip-flops, okay, and signal A, clock A is going to this flip-flop as well as this flip-flop. So node A is common point in the time for this circuit. Node B and C are not common because they have different drivers in the path. Okay, B1 and B2, these are the two drivers, different drivers. And naturally loading on B and C can be different. They also can have different line lengths. As you can see, the physical line length is different over here than for this flip-flop. Parasitic capacitance also will be different. So lines on schematic are not ideal wires. Hence B1 and B2 will not track 100%. It simply means that if the signal occurring at the same time at the input to B1, the outputs may not be synchronized. Okay, output will not be exactly synchronized in time. So this is what has happened. For two different part delays, you have the clocks appearing at different times. So this is clock 1 and this is clock 2. You see here what is happening? There is a slight shift in the clock itself. Okay, this is called as a clock skew. What are the causes of clock skew? Wiring delays, capacitance, and incorrect design. Okay, as you can see here, the clock, see the path over here is too long as compared to this. So clock will arrive here slightly later than the clock arriving for the FF1. What are the effects? How is it going to affect our system? Obviously, the very first thing is it gives incorrect output. Okay, consider the circuit shown on the previous slide, this one. Here if the data changes, then it is reflected by change in Q1 after the positive edge of the clock. But since clock edge of FF2 is late in form of the clock underscore S, FF2 input will see a change input. That is the asserted value of Q1 and will assert Q2 also, which is in fact wrong. So what is going to happen is you are going to get different values at the output. So if there is no clock skew, this is what is expected. Okay, but if clock skew is there, this is what is going to happen. So we get wrong outputs first of all. Again, clock skew may cause violation of setup and the hold times. Consider that the output of flip-flop 1, that is Q1, changes after the propagation delay of the clock to output FF1. So it will change after this one. Okay. If the skewed clock positive edge appears such that Q1 transition falls in the metastability window, you know what happens. The flip-flop 2 output will go into metastable, and that is the reason why it may go into unpredictable state. What is the remedy for clock skew? The remedy is you can use longer flip-flop propagation delay, explicit combinational delays. So you can introduce some delays so as to balance the delays, shorter or even negative flip-flop hold times. So the design of flip-flop has to be such that the hold times are shorter, and use of opposite edge clocking. But obviously this is going to cost you time because you have to divide the clock by 2. Typically, it's not an issue for shift registers. Additionally, the clock will run at half speed, saving power. So obviously, clock skew is cannot be solved directly. So there are various ways in which you can do it. The use of two-phase clocking at the cost of setup time again, or properly design the clock signal path. Okay, so that was all as far as the introduction to this FSM, finite state machines, is concerned. Next, what we will do is we will take up, let us say, the state machine design using VHDL. So you already know that there are various things to be considered. Okay, let me just switch over to the other slide. Okay, is this visible?
Yes, sir.
All right. So let us start with the state machines now. Finite state machines constitute a special modeling technique for sequential logic circuits. Such a model can be very helpful in the design of certain types of systems, particularly when we have a well-defined sequence. Examples are counters, digital controllers, sequence generators, detectors, etc. Now there are the three basic categories of state machines. The state machine is nothing but a combination of combinational as well as sequential logic circuit. Okay, so there are three basic types. One is called as a clock synchronous circuits. One is called as feedback sequential circuits, and the third one is called as the asynchronous circuits. Now in clock synchronous circuits, you have multiple inputs which can change at arbitrary times, and so is the output, but state change will occur only on the clock. So clock is the deciding factor there. That is the reason why they are called as clock synchronous circuits. So all the states are synchronized by the clock. Inputs can change one at a time. Here, this feedback sequential circuits, again, this is out of scope for us, as the asynchronous circuits. This is interesting because asynchronous circuits we have it is a clockless machine. Okay, and for systems where very high speed is required, you have to go for asynchronous circuits. Here the flip-flops are absent. In asynchronous circuit, sequential circuits, flip-flops are absent, but combinational circuits will have some feedback. These are the types of state machines. Two types basically: Mealy machine, you must have done this in your lower classes, and the Moore machine. Please pronounce it properly. It is not Moore machine, it's Moore machine and Mealy machine. Okay? What is the difference? Tell me. Tell me what is the difference?
Input is directly fed to output for output logic
Input
in
is
mill machine.
fed to output. A little bit more elaboration. The output is generated as what? Combination of input as well as the current state. Remember this, input as well as the current state. Whereas in Moore machine, the output is based only on the current state. This is the major difference. Are you getting this?
Yes, sir.
So outputs depend on state and inputs. In Mealy machine, output depends on state only in case of Moore machine. Now, my obvious question is, which one is better? Moore machine or Mealy machine? Which is better?
Since even input is considered, means in output is function of input as well as states in milli, so it has to be better probably.
Well, you cannot have a single answer like that, a crisp answer. It depends on the application. But Mealy machine, even though it may seem a little bit attractive from the point that the output will depend on, obviously output here in Moore machine also is dependent on inputs also, no? Indirectly.
Yes, it does.
Obviously. So the current state is generated based on the inputs. But here, what is the basic difference is that the output will be available, or let us say output will be generated anytime irrespective of the appearance of the clock. Are you getting this? See, because this clock signal is responsible for changing the state. So in between the two rising edges of the clock, assuming that it is a positive edge triggered flip-flop, in that case, even if the input arrives, the output is still going to change, irrespective of the appearance of the clock. Are you getting this? Whereas in Moore machine, output will change only with the clock. Are you getting this?
Yes, sir.
So which machine is more susceptible for metastable issue or metastability? Which can cause metastability? Which machine is susceptible? Yes? The Mealy machine. See, the output can change any time. And if I am having interfacing of this output signal to any other further circuitry which is having a flip-flop, what is going to happen? the input to that next flip-flop will happen anytime, will occur anytime. The change will happen anytime, irrespective of the clock. So there is a chance that there will be metastability for the cascaded circuit. Are you getting this?
Yes, sir.
Whereas in Mealy machine, in Moore machine, it will be guaranteed that there won't be any asynchronous events at all. Everything happens on the clock. The same clock will be fed to the cascade circuit. And so you will never have the problem of metastability there. But what is lost if you try to make it metastability proof using Moore machine? What is lost here? The immediate response to a changing input will be lost. The output will be generated, but only at the appearance of the clock signal. So we cannot directly say which one is better. It depends on the application. If you require that there should be no latency of even half a clock cycle between the input and the output, in that case, Mealy machine is preferred. Whereas if you want a very robust system where metastability issues are very, very less, or maybe can be handled nicely by the clock, in that case, you can use the Moore machine. Is that clear?
Yes, sir.
Okay. So these are typically edge-triggered D flip-flops. So these are the basic topologies for state machines. In theory, both are equivalent. So one can convert a synchronized digital hardware design from a Mealy to a Moore state machine or vice versa. The Moore state machine generates output based on, we have already said, on its current state. Hence, Moore machine output is usually synchronized. Okay, in Mealy machine, output depends on both, and so the output is not synchronized to the clock, or may not be synchronized to the clock. Because the Mealy output based on the input, the correct initiating output process in the Mealy machine is first to change the input value. Due to the dependency of input and the current state, Mealy machine output changes next. As I said, Moore machine output will coincide with the state changes. So this is how the state machine will look like. Understand this state machine properly. State diagram. So a state machine in the form of a state diagram. We will go through this very carefully, because unless and until you understand what is a state machine and how to draw the state diagram, you will not be able to write the design for that. Okay. I think we'll stop here for today. Is that fine with you, guys?
Okay, sir.
We'll continue with this discussion tomorrow. It's going to be a little bit more interesting than whatever we have seen in the past few days. So please make sure to attend the lectures.
Yes.
As far as
Okay,
the
sir.
finite state machines are concerned. All right.